So, momentum practice, free response questions. I always mess that up. Second set, problem 6, last one. And as far as I go, this actually is a relatively straightforward problem. The only thing is that it throws in springs, and so we have to deal with some stuff at the end, but that's good. It's a good refresher for us because it's been a long time since we've done springs. But in the beginning, they give us an object's mass, and they give us its velocity, and they ask us, what's its linear momentum? Oh, I can do that. Yeah, I'm good. Yeah. Momentum is, its linear momentum is going to be its mass, 0.20 kilograms, times its velocity, 3.0 meters per second. That's going to be 0.6 kilogram meters per second. I got it. Piece of cake. All right. What's its kinetic energy? Whoa, throw me a curveball. That's not that hard. Kinetic energy is 1/2 mass, 0.2 kilograms, times its velocity squared. .5 times 0.2 times 9, boom, it's 0.9. Alright, so it's got a kinetic energy of 0.9 joules. Like I said, they're not making it too hard for us yet. Then they hit. This is an unstretched or uncompressed spring. It's got a spring constant here. Alright, but these two blocks hit. And right after the impact, it's as if the spring doesn't exist. We need to find, just through collisions, they stick together. We need to find their linear momentum. So it's an inelastic collision. So the momentum before has to equal the momentum after. The momentum before, we found a moment ago, is 0.6, I believe. Yep. Kilogram meters per second. The momentum after is the sum of their two masses. Now that's going to be 0.2 plus 1.3. So I get that to be 1.5 kilograms times this final velocity that I don't know. Well, actually, wait a second. Oh, hell. We didn't even need to do all this. Well, we will for the kinetic energy, I think. But, folks, look at the question carefully. What's their momentum after the impact? Well, it's the same as it was before. So the correct answer to this is 0.6. Done. Now, we're going to need to find this velocity, I think, to sort out the kinetic energy issue. But I was all going crazy, but they don't ask me for the velocity here. They ask me for the momentum. And conservation of momentum says it's the same. So you do this one in like a split second. Now, this actually becomes part of how to find that kinetic energy, because I need this velocity. So this velocity is going to be 0.6 divided by 1.5. Alright, and that final velocity of the two combined is 0.4 meters per second. Alright, so the kinetic energy afterwards is going to be 1/2, 1.5 kilograms, because it's combined, times 0.4 squared. Alright, so I got 0.5 times 1.5 times 0.4 squared equals, so 0.12. So I have a kinetic energy of 0.12 joules. Definitely an inelastic. It had 0.9 before. It's down to 0.12 joules. Okay. Now we finally get into some of the spring stuff. Determine the amplitude of the harmonic motion. Well, here's what you want to keep in mind. What we know, and this is why this is important, those two blocks have a kinetic energy, in other words, they're moving, and they have a kinetic energy of 0.12 joules. They're going to go until that 0.12 joules of kinetic energy is all in spring energy. And that's when they're going to stop. And whatever distance that is going to be the amplitude. So let's take a look at the whole thing from energy. So when the kinetic energy at the first, at the start, right after the collision, is going to equal the spring potential energy when it's fully compressed. All right. Well, that kinetic energy at the start is the 0.12 joules that they had us find a minute ago. The spring energy is 1/2 k x squared. Oh, wait a second. K they give me. It's 100. The only thing I'm missing is x. Once I solve for x, this is the fully compressed version, so this x will be the amplitude. So let's see, I got to go half of 100, so 0.12 joules equals 50 times x squared. So 0.12 divided by 50, and then take the square root. 0.049. So x equals 0.049 meters, or 4.9 centimeters if you want it. So the amplitude, 0.049 meters. That would be the x value when all of the kinetic energy that it had was turned into spring energy. Determine the period of the harmonic motion. All right, so you got to look through your equation sheet for the period of a spring, not a pendulum. It is going to be, I'm doing this from memory, there's a square root involved, I know that. I can't remember if there's a 2 pi out front here or not, but I do know that it's either K's involved, and the mass is involved. Well, let's see what we make it. If a K is large, the period should be shorter. So I'm going to go K down here and mass above here. I can't remember if there's a 2 pi or something out front here. I should know that. And I was, in fact, correct. I'm not going to lie. I paused it and double-checked. There is a 2 pi in front. So the period of that harmonic motion is going to be 2 pi times the mass, which is the square root of the mass divided by k, which is 100. Let's see. So this is going to be 1.5 divided by 100. Take the square root. And then multiply by 2. And then by pi. And I get a period of 0.77 seconds. But that's an equation you would have been able to look up straight away. All right, in the on your equation sheet. So don't get on my case for not remembering that there was a 2 pi there. I figured it out. But yeah, you should hope that they give you one this easy. You should really, you should hope they give you one this easy.